Okay. All right, let's go ahead and get started then. So yesterday we were talking about really what's called the Introduction to Thermodynamics. So we had a problem or a couple of problems where we used this equation here. Okay, delta U is equal to Q plus W. And so essentially the idea is that you've got something which we call a system. And the system in the examples that we looked at were gases or mixtures of gases. So sometimes we call the system. Sometimes we call it the gases. Sometimes we call it the reaction. Okay, those are all meant to refer to the system. The system has something around it, which is typically a water bath. So there's usually water surrounding the system. Okay. And essentially the way we're looking at this is that energy can go into or out of the system. So it can go both ways. It can come out of it, or it can go into it in the form of heat. Heat transfer, which is Q, or it can go into or out of it in a separate way, which we call work. Now, work is a mechanical phenomenon. It's when you move something. So if you compress the system, you compress the gases of the system, that's doing work on the system. If the system expands against the atmosphere or pushes a mass higher up against gravity, that's doing work on the surroundings. The system is doing work on the piston. Sometimes it's referred to that way. So essentially what we're claiming is there's just two different ways in which you can add or take away energy from a system. And we are interested in knowing how much energy we add or take away from the system. And that sort of bookkeeping is delta U. Delta U is a measure of how much energy is going into or out of the system. The reason that we are at all concerned with this is that we want to be able to figure out how much energy something has to offer to move a device, essentially. So if we want to use this energy to move an automobile, or we want to use this energy to heat up a room, we need to be able to account for how much energy is being put in or taken out. However, there's two ways in which energy can be put in or taken out. One is through heat and one is through work. So we need to have both of those kind of understood. We need to be able to measure both of those so that we can find our delta U. Okay. And so that delta U is referred to as the change in, I'll put this in parentheses, I'll put in parentheses, internal energy. So generally the ALEKS problems, they don't call it internal energy, they just call it energy. The change in energy is, okay? But the technical term for it is internal energy, all right? So you'll see both of those. The textbook uses internal energy, and then ALEKS uses energy, all right? So what I want to do today is build upon that. Remember, this is our sort of the typical problem is a gas cylinder, and you have a piston which is pushing down on the gases, or the gases are pushing up against the piston, okay? The next stage is to look at something called enthalpy, okay? So what I'm going to do is I'm going to give you a little introduction into enthalpy, and then we'll look at some problems. There's essentially two types of problems that we deal with enthalpy. They're a little different from each other. One is kind of looking at it from a chemical perspective. So we'll look at chemical reactions. The other one is more of the piston type problem. So let's talk a little bit about enthalpy. Typically, when we run chemical reactions, we run them open to the environment, okay? Meaning that, for example, you might have a cylinder here, a beaker, and you're reacting an acid and a base. And if you remember, an acid base can react, they form water and a salt, right? When we run that reaction, the lid, there's no lid on top. We just open it up to the environment, right? What that allows to occur is it allows heat to transfer out of, so if this reaction is exothermic, if it gets hot, the heat can transfer out very easily. Heat can come in. So if the reaction is endothermic, it'll feel cold, so heat will go into the reaction. Okay, so heat can kind of go both ways, right? And so one aspect of that that's important for us is that if we're open to the environment, we have air up here. And air has what we call a pressure, called air pressure, right? So if you've ever flown in a plane, you're aware of that. If you've ever driven up a high mountain, you're aware of that. That as you change altitude, the pressure of the air changes. The ears are sensitive to that, right? So air pressure. So I'm going to use the symbol P for air pressure. And to be a little more technical about it, a little more scientific about it, we won't call it air pressure. We'll call it atmospheric pressure or external pressure. So either external, which means from the outside, or atmospheric pressure. Okay. Now, the significance of this is that when you run a reaction, that pressure from the atmosphere is constant. It's pushing down. The air is pushing down on the liquid where this reaction is occurring. And generally, what we can say is that this external pressure, P, is constant. It doesn't change. Okay, it's unchanging. And there are many examples of reactions where that's not the case. We would look at those separately. Right now, we're just looking at the case where the atmospheric pressure doesn't change. So obviously, you wouldn't run this reaction while you're flying, changing your altitude, because the pressure would be changing, right? But if you're in a room, the pressure of the air is pretty constant, no matter what happens with the reaction. Okay. Now, the significance of that is this. If that is true, if the pressure is constant, then we can make the following claim. We can claim that any work done by the reaction, the system, is equal to negative, so I'm going to make sure you have this negative here, the external pressure, I'll just put P for external pressure, we'll assume that that means external or atmospheric, times delta V, where delta V is equal to the final volume minus the initial volume of the system. So this refers to the system. Okay, so for example, if I have a container and you have a gas in there, could be more than one gas, we'll just say it's one gas for now. And then what happens is a reaction occurs or some sort of process. And now the volume changes, right? So obviously it's taking up more space. If it is the case that the pressure, the external pressure is constant, so if the pressure pushing down from the atmosphere is constant, then what we can say is that the amount of work that the gas did on the piston or on the surroundings is equal to minus the pressure that's being applied here, so that's the atmospheric pressure, times delta V, which would be the final volume minus the initial volume, okay, minus P delta V. That's an important equation. So this allows us to calculate the amount of work very easily. All we have to do is make a measurement of the external pressure, which might be called a barometer we would use to do that, and then multiply that by whatever the difference in those two volumes is, the final volume minus the initial volume. Okay. Now, I do want to make sure that when you do these problems, you get the right number. So there's a little conversion factor here. And the reason the conversion factor here is that pressure is typically given in the units of atmospheres. And we haven't talked about gases yet. We're going to go through pressure conversions and when we talk about chapter 10, but volume is typically also in liters. However, the units of energy are typically not in atmospheres and liters. They could be if we wanted them to be, but generally we don't do it that way. So what happens is you need a little conversion factor, and I'm going to write it down here. And the conversion factor is that 1 atmosphere liter is equal to 101.3 kilojoules. I'm sorry, 101.3 joules. Not kilojoules, but joules. This is just a little conversion factor you'll need to do these little problems. Okay, so I'm going to show you an example of this right now. So let me see if I can find it here. Here we go. So this is called calculating pressure volume work. Okay. All right. So in this question, it says that you've got a mixture of xenon and hydrogen gas. So you have xenon and hydrogen gas. And it's expanded to a volume of 55.0 liters to 91.0 liters. Okay, so that's the expansion of a mixture of gases. The pressure is held constant. Turns out if the pressure changes, this is a completely different problem that we don't cover here, at 48.0 atmospheres. Okay, and it says just calculate the work done on the gas mixture. Okay, so it's expanded and then the pressure is held constant. So some of the keywords there is it's expanded. That means the volume's getting bigger, right? Compression is when the volume gets smaller. Obviously, they give you the numbers there. Those are your volumes. And then they say that the pressure is held constant, 48.0 liters. We could solve it if the pressure wasn't constant, but it would not be one that we're going to look at in this course, okay? So it says to calculate the work done on the gas mixture, okay? Well, since the pressure is constant, we can use this equation here, minus P delta V. Okay, so this assumes that the pressure is constant. Okay, so now let's go ahead and take a look at it. Just to kind of give you an idea of what's happening, you have this gas. It's a mixture of gases. The volume is 55, right? 55.0 liters. There's a pressure downward. So this is obviously not atmospheric pressure. There's something pushing down really hard. It could be a mechanical device or something like that. And that pressure, that external pressure, is equal to 48 atmospheres. Okay, then what happens is the gas expands. They don't say what causes it to expand, but it essentially pushes the atmosphere up. So now we have a larger volume. Oops, liters. Again, it's pushing against this atmosphere. It takes work. It takes energy to push something away, right? So if you have something over your head that you're in the gym, you're working out, you're pushing weight above your head, that takes energy to do that, right? We call that work, the movement of that object, okay? So all we need to do is just figure out, plug these numbers in. So our work would be minus, and then we put in our pressure. So I'll put the pressure in parentheses here, 48 atmospheres. And then V final minus V initial. So the final volume is 91 liters, and the initial volume is 55 liters. Okay, so there we go. So let's go ahead and calculate it. So 48 times 91 minus, let me come back over here, 91 minus 55. And it looks like we get about 1728. And then our units are, we have atmospheres here, and then this is liters here, so atmosphere liters. Okay, so there's our answer in atmosphere liters. Typically, we would want to have it in joules, however. So we would take our 1728 and the conversion factor is 101.3 joules per 1 atmosphere liter. And there's our atmosphere liters. Okay, so 1728 times 101.3. Now you get this really big number, 175,000. Okay, and then we would be joules. So that's a big enough number that we would really want to kind of cut that down somehow. So how would we do that? We could either use scientific notation. We could put it into scientific notation. By the way, all the numbers have 3 sig figs. So it looks like our answer would want to have 3 sig figs here. So that would be one thing we could do. We could either put in scientific notation, or we could use a prefix. So what I'm going to suggest is that let's try both. We have 175,000 joules. So let's put it into scientific notation. The decimal point is right here, so I'm going to move it to the left. 1, 2, 3, 4, 5. I'm going to move it 5 places. Left is positive, lip. So if I move the decimal to the left, it becomes positive. So 1.75 times 10 to the 5 joules. So that would be one way to do it. Another way to do it would be to say, well, what would be a prefix that is in the thousands? Kilo is in the thousands, right? Kilo is 1,000. So why not do it this way? You have 175,000. Let's do kilo. 1 kilojoule is 1,000 joules. So just divide it by 1,000, you get 175 kilojoules. By the way, there's a negative that I forgot to put in there. Right, we have a negative in there. Yes, very good, Nicole. You caught it. Negative 175. So one of the things that I find kind of interesting about the problem was the wording of the question. It actually, if we go back, let me just save this. When we go back to the original question, it says, calculate the work done on the gas mixture. And the answer is the gas mixture didn't have work done on it, which is sort of interesting. The gas mixture actually did work on the piston, did work on the cylinder, on the surroundings. So it is negative, absolutely. So let me write it over here. Negative 175. Good. So it's sort of odd wording. I'm not sure why they said. I mean, I guess if you say it's negative, you're saying that the work that was done on it is negative, so it did work on the surroundings. But if I were to write that question, I would phrase it a little different. I would say, calculate the work done by the gases, or done on the gases. But here they said done on the gas, and it was actually not done on the gas. The gas actually did work on the surroundings. Okay. So there you go. So that little conversion factor, 101.3 joules per atmosphere liters, you could write it either this way, 101.3 joules per 1 atmosphere liter. Or you could use this one, 0.1013 kilojoules, right? I'm just moving it over 3 places. Oops, per atmosphere liter. Let me just make sure this is in. Oh, it's on. There we go. Okay. All right. Either of those will work. Generally, what happens is when you do these problems, the numbers you get in joules are pretty large. They're in the thousands. So it is common to just go ahead and convert them to kilojoules. So if you want to save yourself a step, you could just use this conversion factor. But sometimes the textbooks will tell you to do this and then say, oh, it's a big number, and then convert it to kilojoules. Most of the examples you do in here are going to be in the thousands. They're not going to be 5 joules or 50 joules, and they're going to be pretty big because this number right here is pretty large right there. It's 100 joules per atmosphere liter. Okay, so that's one problem where we're dealing with work. It's pretty straightforward. I don't think, let me just take a real quick little look to see if there's any that are any different. Sometimes they say it's compressed. So remind yourself, if it's compressed, meaning the gases, from 99 liters to 96 liters. So suppose they tell you that right there, it got compressed from 99 to 96. Then if you think about it, the final, it got 2, right? So the final is 96. And the initial would be 99. So look what happens mathematically. You get 2 negatives in here, right? You have the negative that's in the equation, right? That's in the equation right there. But you can get a negative for delta V. So as long as the final volume is smaller than the initial volume, you're going to get a negative value there. And that's perfectly fine, because what ends up happening is the negative times a negative is a positive. Right, so you're just going to take your P, the pressure, multiply it by whatever that difference in volume is, but it'll be positive.
Actually, me too. I woke up pretty easy. Yeah. Yeah. What are you doing now? Are you working yet?
Okay, all right. So there you go. Let's take a look at enthalpy. Okay. And feel free to unmute yourself if you have a question. Okay. All right, let's take a look at enthalpy. Enthalpy is used by chemists quite often. So let me talk a little bit about enthalpy. The symbol for enthalpy is an H. Okay, capital H typically. And enthalpy is analogous to internal energy. It's a measure of the energy in the system. Okay. So a system, like let's take, if you look at a balloon has all these air particles bouncing around in it, right? All of those molecules are moving around, so there's kinetic energy. The atoms in the molecules are interacting with each other electrically, so there's potential energy as well. And the molecules are vibrating, vibrating like springs. They're rotating. All of those different forms of energies add up together to give you the internal energy. The internal energy is the measure of how much energy something has. But now we're going to look at something called enthalpy. And the reason that we look at enthalpy is that it's a convenient thing for us. So what I'm going to do is I'm going to define something called enthalpy as being the internal energy plus PV, where P is just the pressure, the external pressure. V is the volume of the gas or the gases. And then U is the internal energy, right? So enthalpy is a little different than internal energy. We're adding this extra term in here. And the reason we're adding this extra term is just for convenience. And here's what we're going to claim. We don't really want to know how much internal energy or how much enthalpy something has. Really what we want to know is how much it changes. And the reason we want to know how much it changes is because of this equation right here. We can measure this, and we can measure this. These are two things we can measure, okay? We haven't talked much about how we measure Q yet, but we just looked at how we measure W, right, at the previous example. Both of those things can be measured. And since both of them can be measured, that means we can calculate this really easily, right? So it'd be like, hey, if I want to know what your body mass index is, your BMI, what do you need to measure someone's BMI? You need to know how tall they are, and you need to know how much they weigh. So if I know those two things, I know their BMI, right? Well, same thing here. If I know what Q is, which I can measure, and I know what W is, and I can measure that, I now know what delta U is. But now what I'm going to claim is that sometimes we don't really want to know what delta U is. We want to know what delta H is. So I'm going to write this. Delta H is delta U plus P delta V if we're at constant pressure. So one of the requirements to deal with enthalpy is that we're at constant pressure, which we talked about it a little bit earlier, that at constant pressure, that's often what we're looking at. We're often looking at reactions that are at constant pressure. Okay, so that's cool. But now what I'm going to do is a little trick, just a little arithmetic trick, a little algebraic trick. I'm going to substitute in Q plus W for delta U here. So now I have delta H equals Q plus W plus P delta V, right? So far, so good. The next thing I'm going to do is one more little trick. It's substitution, right? And the substitution is a very simple one. If you remember in the previous example, what did we say? We said that W is minus P delta V, right? So I'm going to substitute that in right here. So I'm doing two substitutions. One is Q plus W for delta U, and the second one is minus P delta V for W. And look what happens. Delta H is equal to Q. Now I'm going to put in our work, minus P delta V. That's why that work problem that we just did is the first kind of one in this section, so that you can kind of see this. So now we have Q plus W, right? I have to put minus because W is minus P delta V. And then I'm going to add in this plus P delta V. Okay, so take a look at what happens. You have delta H is Q minus P delta V plus P delta V, that's 0. Those two subtract out, they're 0. So now we have something really, really simple. And so this definition of enthalpy, there's nothing mysterious about it. It's just a little trick that we're doing to make the problem simple. It turns out that if we are at constant pressure, and there's another requirement, which is that the change in volume is not very big in the process. And so I'm going to put that if delta V is small. Okay, sometimes that's not the case, so then we can't really do this, but much of the time we can. If that is true, then we have really, you can't get much simpler than this, right? So if you heard that chemistry classes have complicated equations, well, this is not one of them, right? It just says that delta H is Q. That's really simple. So sometimes we put a little P down here to remind ourselves that it's at constant pressure. So if you see a little subscript P, that just means it's at constant pressure. Okay. There's a similar one that we're not going to go through, which says that delta U is equal to QV. So if you're at constant volume, you can figure out delta U very easily. It's just Q. Okay. But this is the one we're looking at right here. All right. So very simple. It just says delta H is equal to Q. So you might ask, well, why do they use H? Well, think about it this way. We'll call it heat, right? H for heat. So enthalpy is often referred to as heat. So you'll see this terminology: heat of combustion, heat of reaction, heat of dissociation. Heat in that context usually means enthalpy, the enthalpy of. But since enthalpy has three, it's a long word, and heat is a very short word, we typically use heat. Okay. So let's take a look at kind of manipulating these things just so you can sort of see the type of problem that we can do. Okay. So this is called understanding the definition of enthalpy. All right, the understanding and definition. So let's take a look. It says in here, measurements show that the enthalpy of a mixture. So I'm just writing down the important parts here. Of gaseous reactants. Decreases by 199 kilojoules during the reaction. Okay. They tell you it's at constant pressure. That's important because if it's at constant pressure, all those little equations that we looked at are valid. Okay. Furthermore, careful measurement, careful monitoring of the volume change shows that negative 176 kilojoules of work is done on the mixture during the reaction. Okay, so I left out a few of the kind of details in there that they put in there that you don't, just to make it a little bit shorter. They carefully monitored the volume change to figure out what the work does. Because remember, the way we figured out work is through P delta V, right? So we know what work is here. Okay. So now the question is, calculate the change in energy. during the reaction of the mixture. I'm sorry, of the gas mixture. Okay, and then they ask you, is the reaction endothermic or is it exothermic? Actually, they put it the other way. They put exothermic or endothermic. Okay, so let's take a look at how we go about this. Let's take a look at what they first tell us. They tell us the enthalpy decreases by 199 kilojoules. Okay, so really what they're saying is delta H is minus 199 kilojoules. Now, how do I know that? Well, it says it decreases. That's negative. When something decreases, that's a negative change. And so the change in enthalpy, delta H, is minus 199 kilojoules. You're not going to see problems where you have to figure out H. You're going to see problems where you have to find delta H, okay, or delta U. You're not going to find problems where you find U. It's delta U you'd be interested in, okay? So the next thing is it says that negative 176 kilojoules of work is done on the mixture. So that means work is equal to minus 176 kilojoules. Now, in that particular case, they actually give you the sign. That's fine. The work is done on the mixture. So in this particular set of problems, they're not going to be as complicated as they were the one we looked at yesterday with delta U. They're going to tell you generally that it's done on the mixture. But in theory, they could say that the mixture of gases did work on the piston or did work on the cylinder. And in that case, you would have to change the sign. But for these ones, they're going to be doing it from the perspective of the mixture, which is the system, okay? So that's the numbers they just gave you. So now it's just a little puzzle, right? We have four things. We have delta U, we have Q, we have W, and we have delta H, right? So those are the four things we've got. We've got delta U, we've got Q, we've got W, and now we've got delta H. These first three are the ones we looked at yesterday. Today, we just added one more, which is delta H, okay? So let's see what they asked for. Calculate the change in energy. And as I said before, when they say change in energy, they mean internal energy. So that's right here, delta U. And so if you take a look at what you have, you've got delta H and you've got W. So they gave you this one and they gave you this one. You don't know what this is, but it's at constant pressure, right? So you actually do know that delta H is equal to Q, right? Because we're at constant pressure. So you actually know that one as well. So there's a couple ways you could do this. So one way would be to say this: delta H is equal to delta U plus P delta V, right? And so you know what P delta V is. You got your work here. Another way to do it would be to say, since we're at constant pressure, delta H equals Q, and we know that delta U is equal to Q plus W. So that would be another way to do it, right? So since we know delta H is equal to Q, we also know we know that value right there, and then we know what W is. We've got the W there. So either way will work. You should get the same answer either way. I'm going to use the second one. I'm going to use the idea that delta H is equal to Q. And since delta H is equal to Q, we can just use Q plus W. Okay? So let me save that. All right. So let's come over here. So delta H equals Q. And so what I should say is actually Q is equal to delta H, but that's minus 199 kilojoules. And then we've got work is equal to minus 176 kilojoules. So delta U is equal to Q plus W, which is minus 199 kilojoules plus minus 176 kilojoules. And that should work. So 199 and 170, well, that's minus 375, right? That one I can do. And there you go. So there's your delta U. Okay, all the numbers were given in kilojoules, so we can go ahead and leave it in kilojoules. And then there's a second question, is it endothermic or exothermic? Well, endothermic or exothermic is Q, right? That's the issue. So since Q is negative, our sign convention is that if Q is negative, that's exothermic, right? And then remember, if Q is positive, then it's endothermic. Okay, and the calculations that we do in this course, in a chemistry course, are generally from the perspective of the system. So that's why exo is negative and endo is positive, is the idea you've got this gas mixture. Okay, you've got this gas mixture. And so if heat is going into the gas mixture, that's positive, right? If heat is coming out, that's negative. I guess I'll write that over here, right? Again, think of it like money. It's like currency exchange. You've got, if money's coming in, that's positive. If money is going out, that's negative. So that's why chemists look at it from the perspective of the gas mixture. Okay, we do the same thing with work. The reason that compressing a gas, so if you do compression, the reason compression is work is positive, the reason it's positive in that case is because when you do work on a gas, you're actually transferring energy into it. The gas has more energy at the end than it does at the beginning. And so that's why it's positive. And that's why expansion is the opposite. Okay. So let me see. I'm just going to take a look at another example. And okay. So when you do this particular problem, what I would do if I were approaching it would be just to kind of like set up a little table for yourself. So the table would be, you've got delta U, you've got delta H, you've got Q, and you've got W. There's your 4 variables that we're looking at, right? And so for this particular problem, essentially what they're going to do is they're going to give you 2 of them, and then you're going to have to find the other 2. But we have this relationship that delta H, if we're constant pressure, which we will be for this example, for this problem you will be, delta H is equal to Q. So in a sense, that simplifies things. What it tells you is that, you know, these 2 are equal to each other. So really then they're going to give you 2 of them, and you only need to find the third. So in the previous example, what they did was they gave you this one, and they gave you this one over here, and then you had to figure out this one because you already know what this one is. Those 2 are equal. But we could give you one where they give you, for example, they might give you the work, and they might give you the change in energy, and then they might ask you for the heat. So in that case, you can still do it because you've got these 2 out here. So that allows you to figure out this one. This one is equal to this one, so that allows you to figure that out too. So as long as you know 2 of them, you're set because you've got this relationship here, which gives you the third one. Okay, kind of cool. The wording, again, what you're going to find when you go through these problems is the wording is involved. These are very long paragraphs of explaining what's happening, but the actual calculation is ridiculously simple, right? I mean, all we're doing is adding 2 numbers together. But the challenge of these is being able to read through that paragraph and figure out what they mean. Okay. All right, let's take a look then at a little bit more about enthalpy. And the main issue here with enthalpy is chemists use it all the time. We use it more than internal energy. So enthalpy is H, change in enthalpy, delta H, which, technically is H final minus H initial. You don't see that very often, but just like delta U is U final minus U initial, this is true with enthalpy as well. You generally don't have to use this equation. We don't use it very often, but we do have this if we're at constant pressure. Delta H is equal to Q. And I'll put a little P there just to remind us we're at constant pressure. So the significance of that, again, is that since we are often running at reactions at constant pressure, that allows us very easily to find the change in energy. You can, even though enthalpy is not technically the same as energy, as internal energy, they're pretty similar, right? So it's essentially a measure of how much energy something has in which heat is being transferred during the process. So you can find delta H. That's how much energy essentially the reaction gained or lost through the form of heat. So in the next type of problem, what we do is we're going to use the general properties. So using the general properties of reaction enthalpy. Okay, so let's take a look. In this particular type of problem, what they do is they give you, now we're doing chemistry, okay? We're doing some chemistry now. They give you an equation. That was a lot of physics and engineering we just did. We didn't really do any chemistry in this chapter yet, but we've finally gotten to it. We're now doing some chemistry. So the products of this reaction, boy, this is going to take a lot of space. I think I can fit the last product in there. And now right next to it, I'm going to write delta H is equal to minus 443 kilojoules. Okay. Okay. So this right here is referred to as a thermochemical equation. Now, what happens if I kind of rotate this? There we go. I'm going to try it this way, okay, you guys? So delta H is equal. There's a disadvantage of doing it in the landscape mode, but that's fine. Okay. Okay, first of all, what I want to do is I want to show you what this thermochemical equation is telling us. It's telling us, this, by the way, is a redox reaction. If you look at the oxidation number of magnesium, it's an element, so it's 0. This is a compound over here. So in a compound, magnesium has a oxidation number of +2. The hydrogen has an oxidation number of +1 here, right? In a compound, hydrogen is +1, with the exception of the hydrides, where it's -1, but that's not a hydride. And then over here on the product side, it's an element, so it's 0. So you can see right there, that's a redox reaction, right? The hydrogen has gone from +1 to 0, so that's reduction. It became less positive, that's reduction. And then the magnesium's gone from 0 to +2, that's more positive, so that's oxidation. There's your redox reaction, okay? Redox reactions are often associated with very large enthalpy changes. And so that's why things like batteries are essentially redox reactions, is because there's large enthalpy changes with those reactions. So here's a large enthalpy change. And this is actually pretty large. Okay, this is as large as a combustion reaction. If you're burning gasoline, it would be around this amount of energy change. So that, this is a redox. So this is called a thermochemical equation. The thermo refers to this. That's thermo, right? We're talking about thermochemistry in this chapter. So negative 443 kilojoules is telling us how much enthalpy change there is. Notice it's negative. That means it's exothermic. Now, the meaning of exothermic is that heat goes out, right? Heat goes out. So from a practical perspective, that means there's energy leaving the system. As this reaction occurs, it's producing energy. It's not actually producing energy, right? Producing is a technical word, but it's releasing energy. It's evolving energy. It's transferring energy to the surroundings. How that gets used is what we do from an engineering perspective. Do we take that energy to heat up a room? Okay, we could do that. Do we take that energy to run electricity? Maybe we're going to do that, right? So how we use that is up to us as humans, but essentially it's releasing energy into the environment, okay, into the surroundings. So here's our balanced chemical equation, and balancing is important in terms of these types of problems. It's got to be balanced. And then we have our enthalpy change here, okay? Those two together, the equation plus the delta H value, if we have both of those, we call it a thermochemical equation. If we don't have the delta H, then we call it a chemical equation, all right? So there we go. So there's a balanced thermochemical equation. So what I'm going to do, let me save that right there, is as I go through this problem, we're going to manipulate it a little bit. Okay. Oops. Let me come over here. And we're going to manipulate it in the following way. So let me just rewrite the equation again. I'm going to leave the states of matter out. We don't need the states of matter to do the calculation. Now, in terms of the value of delta H, the states of matter are important, but we don't need it for this particular example, okay? So what we're going to do in this problem is we're going to manipulate the equation, and I want to show you what happens to delta H when you manipulate the equation. So in this example, the first one, the first thing we do is we're going to see this equation that looks similar to the one we have above, but it's different. Oops, sorry, I made a mistake there. It's 2HNO3. There we go. And they want us to find delta H. Okay, so take a look at this second equation, and what you're going to do is you're going to compare it to the first one. Okay, so if you look at the second equation here, it has MgNO3 2, just like the first one does. It has H2, just like the first one does. It has 2HNO3, just like the first one does, and it has Mg. So everything is the same, but it's reversed. This is called a reversion, or reversed, a reversal, actually. So this reaction is reversed. It's the opposite of this one. Whatever was a reactant here is now a product here. Whatever was a product here is a reactant here. Everything else is the same. The states of matter are the same, the numbers of them, nothing else has changed. It's just been reversed. And again, you can think of energy like money. So if I said I gave you negative $200, you might kind of be confused by that. But if I say I gave you negative 200, that means I took $200 from you, right? I did the opposite of, so the negative means the opposite. So if we reverse an equation, so let me put it this way, reversing a chemical equation, what it does is it changes the sign, meaning plus minus, of delta H. That's all it does. Okay? So in other words, if it's positive coming in, it's negative going out. So we reverse the equation, so all we do is change the sign. Right? Now it becomes positive 443 kilojoules instead of negative 443 kilojoules. Very simple, right? So when you look at these problems, just be careful to take a look and make sure that the coefficients are all the same. Just see if it's the products are now the reactants and the reactants are now the products. All you got to do is change the sign. That's all. Okay. Now, there are other changes you can make as well. So in the next one I want to show you, what they do is they say, okay, now we have HNO3 plus 1/2 mg goes to 1/2 mg NO3 plus 1/2 H2. And again, they want you to determine what delta H is. Okay. Now, take a look at this one. I like this example because it kind of, it validates what I said back in chapter 3, which is that fractions in balanced equations are perfectly fine and often preferable to whole numbers. So here's a good example of that. You've got a half in 2 of the materials, or 3 of the materials in this reaction. Only one of them actually has a whole number, and that's the HNO3. So it's perfectly fine to have fractions. Now what we have to do is we have to figure out, what did they do? So again, just go through each thing. You've got HNO3. You've got HNO3. It says they haven't changed it. It's still HNO3. It's Mg. It's Mg, so they haven't changed that. MgNO3 that's the same. And H2 is the same. So everything's the same in this third reaction compared to the first one, with one difference. The coefficients are different. So they've done something to the coefficients. So now we just have to figure out what they did to the coefficients. They haven't reversed it, right? It's still HNO3 and Mg on the reactant side. So what have they done? What they've done is they've taken 2 and they've turned it into a 1. Well, what do you do mathematically to turn 2 into a 1? One way to think about this is you multiply it by something. Okay? If you multiply 2 by something to get 1, what did you have to multiply it by? You had to multiply it by 1/2. So it looks like what they did was they took this 2 and they multiplied it by 1/2 to give us 1. So let's see if that works for the other ones. Here we have a 1, and we have to multiply it by something to get what we have down here, which is 1/2. Well, what do you multiply by 1 to get 1/2? You multiply it by 1/2. So what they've done is they've multiplied both of these coefficients by 1/2. And it turns out if you go through all of them, you'll see it's the same thing. You know, to go from 1 over here to 1/2, you have to multiply it by 1/2. So really what they've done is they've taken this whole equation and they've multiplied it by 1/2. Everything by 1/2. And when you multiply everything by 1/2, you get HNO3 plus 1/2 Mg to 1/2 MgNO3 plus 1/2 H2. Okay? And so they multiply by 1/2. So here's our rule. Whatever you multiply the equation by, you multiply delta H by the same number. So if we multiply the equation by 1/2, so this is for the equation, that means you multiply by 1/2 the delta H. You multiply delta H by the same value, the 1/2. So if we take negative 443 and we multiply by 1/2, you get negative 221.5, which I guess you could round it to negative 222. So negative 222 kilojoules, and there you go, right? So all you got to do for that one is just, you know, notice that the reactants are on the same side, the products are on the same side. They haven't changed those. They've just multiplied by some number. You just have to figure out what they multiplied them by. Okay, they're going to multiply it by 1/2. They're going to multiply it by 1/3 or 1/4. They might multiply it by 2 or 3 or 4. You just have to figure out what that fraction is, what that number is. And then keep in mind, they're not going to multiply one reactant by one number and another reactant by a different number. They have to multiply the whole equation by the same number. So once you've figured out what they did to HNO3, it's going to be the same for all the others. So you don't have to go do all of them. You could do 2 of them to check to see you get the same number, and that would be a good idea, but it's going to be the same. You can't have mixed multiples, okay? Now the last step would be that you could do both together. You could multiply by a number, and then you could also reverse it. So sometimes we'll have that. So suppose we have, I'm going to write this again. You have 2HNO3 plus Mg goes to MgNO32 plus H2, and our delta H is minus 443 kilojoules. Now suppose we end up with this one, 3MgNO32 plus 3H2 goes to 6HNO3 plus 3Mg, and they want us to find delta H. Okay, what they've done here is 2 things. They reversed it, and they also multiplied by some number. So how do I know they reversed it? HNO3 and Mg are reactants here. HNO3 are products here. So that means they reversed it. That's the easiest thing to check. So if that's true, you change the sign. But there's another difference too, right? The coefficients aren't the same. So if you take a look, our HNO3 here was a 2. Now it's a 6. So what do you have to multiply 2 by to get 6? Well, 2 times 2 is 4, 2 times 3 is 6, right? So that means they multiplied it by 3. So they also multiplied by 3. And again, you don't have to do them all. You can do 1, or you can do 2 to check, or you could do 3, or you could do all 4 if you want to check just to make sure. But whatever they multiplied the HNO3 by, they're also going to multiply the Mg by. And you can actually see that, right? Because if you think about it, Mg is 1, now it's 3, so they multiplied it by 3, right? So there's a good check. So what did we say? If you multiply if you multiply the equation by 3, you multiply delta H by 3. Now we already changed the sign, right, because of the reversal. So now we just got to multiply that by 3. So 3 times positive 443 kilojoules. We're now going to get, what is that? I'm not sure. 443 times 3. 9, 12, 12, 13, right? Looks like 1329. So 1329 kilojoules. Now there is a sig fig issue. I guess you could say it's 1330 kilojoules. But, then Alex is going to give you a problem because it's going to want you to put the decimal point. So 1.33, 123 times 10 to the 3 kilojoules. And that's a way to get out of the sig fig issue, because now we've got 3 sig figs. Okay. So there you go. So 2 changes. If they reverse the equation, change the sign. If they multiply the equation by some number, multiply delta H by that number. And if they do both, do both. Okay. And let's see. So that is, I'm going to end it here because we're out of time. We have one more enthalpy type problem from section 5.3 to handle. So we'll deal with that tomorrow, and then we'll get into calorimetry. And then really after that, all we have to do is the standard enthalpies of formation, and we'll be set. Okay. So have a great day. Have a great, actually, today's Thursday. So on Tuesday, we'll come back and we'll keep working on this. So have a great day. And then also have a great weekend. Reach out to me if you have any questions.